Okay, so we can start, right? So in the previous class, we started discussing scattering, right? Which is pretty much the major goal in this central force problem in this semester, right? Then after this, we will discuss a little bit the circular orbits, the stability, their closeness, and so on, and pretty much that will be the end of this chapter. But anyway, so back to scattering. So in the previous class, we sort of stated the problem. So we draw a big picture. Then I decided not to reproduce it. You have in your notes. I don't need it desperately. I will not need it really today. So we will just need some formulas from that. Right. So what we introduce, of course, we introduced the two major parameters, the impact parameter and the scattering angle. Of course, we discussed that they are not independent, they are dependent. And of course, the theta we decided to treat as being independent, right? Because theta you can measure, and S is too small in order to measure it experimentally, right? Of course, you can use it theoretically, but experimentally it's out of our reach, right? So that's why theta is better from the practical point of view. Then, so we decided that we're going to send a wide beam of identical particles, right? So identical, it means the same mass, the same total mechanical energy, which you provide in your experiment, basically, right? And then we made two assumptions. First assumption, we assume that particles are not going to be absorbed, right? So all orbits are going to be unbounded. So sort of like a parabolic or hyperbolic orbits, right? So none of the orbits are going to be circular or elliptical, right? After a particle will interact with the scattering center. And the second, we assume that the scattering is going to be elastic. Basically, total mechanical energy is conserved, right? And after that, we defined intensities, intensity of incident particles and intensity of scattered intensity, right? And after that, we ended up writing down this number of particles dn prime scattered, right? We wrote it as I prime. It's the intensity of scattered particles. Basically, it's a number of particles per unit time per solid angle, per unit solid angle, and then multiplied by d omega, right? So that's what we got in the previous class about the scattered particles. And then for incident particles, number of incident particles, right, per unit time in dA. Basically, remember dA, it's that thin ring, right? Thin cross-sectional ring. And we wrote that it equals to the intensity times dA. So it's a number of scattered particles per unit time in d omega. So this is number of incident particles in unit time in dA. Okay, so now then we introduced the differential cross section, and we introduced it in this way. So I prime equals to sigma. You know what? Let me write the dependence. Of course, this sigma will be eventually will depend on theta, on scattering angle, times I, right? And a few words about this. So sigma by itself, it doesn't give us number of particles. No. Where are number of particles? I prime intensity, it's a number of particles per unit time per solid angle. So this is number of particles. Here number of particles, but of course incident, in the incident beam, right? This not. But since this is basically a constant in your experiment, right? You build your, I know, some accelerator, right? You pick some particles, you accelerated them, you shoved them on the scattering center. So this is some kind of a given number or given parameter in your experiment, right? So here there is no dependencies on nothing, right? Not on anything. So all angular dependence, all information about how particles are going to be distributed on your detector is here. Here, right? So again, it doesn't give us number of particles. It has all information about the distribution of particles on our detector's position on the sphere, right? You remember? So the product sigma times I, yeah, it gives us a number of particles, right, distributed on detectors. But sigma by itself, it's not number of particles, right? But at the same time, it's actually it's useful that sigma is written in this way, that I is not involved, because different research group can do slightly different experiments and their eyes can be different, right? So it's better to have some parameters independent of your experimental setup. So you can compare results obtained by that group, by this group, by you, right? So that's why sigma is kind of practical, useful, right? That it doesn't depend on intensity of the incident beam, right? Okay, so that's what I wanted to mention. And now, okay, probably I should frame this because this is important. And now, as I told you at the end of the previous class, let's get the expression or let's get a definition of differential cross-section, which the book offered. Okay, so um, let me write. So let's get book's definition. Book's definition of sigma. Okay, so in order to do that, we're going to multiply this by d omega. Right, so it will be I prime times d omega equals to sigma times I times d omega. So I prime times d omega, it's this number of scattered particles per unit time in d omega, right? So I can write it dn prime scattered, right? And so now basically now let's just rewrite in the proper form. I will just write sigma times omega over here, sigma times d omega, and then it will be dn prime scattered divided by incident intensity. So basically that's how Book defined differential cross-section sigma. And of course, Goldstein wrote in words. Basically, it's this number of particles in, okay, per unit time. Let me write per unit time, per unit time in d omega, in d omega, and divided by the incident intensity, incident intensity. Right. So that's how Book defines differential cross section. Okay, I can sort of frame. Right. Okay, for me, when I started reading the book, right, I cannot say that I was a big fan of this definition, right? Maybe you will find it more useful, right? When I rewrote or rework in this way, okay, introduce sigma, for me it sounds better, but of course it's up to you, right? Because again, as you saw, this follows from that, and of course from this you can get that. So basically, these are the same thing, but presented in a different way. In my opinion, of course, my very subjective opinion, right? This is easier to comprehend, to understand, right? Okay, so that's about the definition of sigma. It should be enough. And now, let's get an expression of sigma in terms of our parameters s and theta. Of course, eventually it will be in terms of theta only. But now we need to get the expression. So let me put new bullet. So let's get expression for sigma, right? Okay, and we're going to use that statement which I already mentioned today, and I wrote it in the previous class, conservation of particles. So number all the particles which went through that thin cross-sectional ring must go through that big ring on our detectors, right? So I can write that this dn, first I wrote probably, okay, scattered. Oh, you know what? Just now I realized this prime shouldn't be there. We define with the prime a different quantity, right? So this shouldn't be with prime. On purpose, I remember I kept prime in the with the quantity which I'm not going to use later. Right? So this prime shouldn't be there. Right? Okay, that's why I kind of started looking, oh, it doesn't sound right. Scattered equals to number of particles, yeah, incident particles, per unit time in dA, right? Conservation of a charge, conservation of particles, right? Of course, only this during this process, because there is no such a thing as conservation of particles, but we assume that, and we're going to use that. Right, so now, of course, we can write it in terms of that. So it will be I prime times d omega equals to I times dA. And of course, I prime, it's a sigma I. Right. Okay, so now we can write sigma times I. Instead of d omega, we're going to use those expressions which I wrote right on the picture in the previous class. Right? You have in your notes, I think I remember them. It's a 2 pi sine of scattering angle theta n times d theta, right? Then this, again, intensity, and dA, I think I also remember it's a 2 pi s ds. So that's, maybe I can put brackets to emphasize that these are d omega and dA. Of course, I gets cancelled, right? And now we just need to rewrite it, sigma, as a function of, okay, theta equals, so, yeah, 2 pi also goes. 2 pi goes, so it will be s divided by sine of theta, and then ds over d theta. ds over d theta. Okay, almost the final form of the expression, except for one small thing. S and theta are dependent, or I already mentioned that several times. And look, how are they dependent? Okay, yeah, what's the dependence? Look, when S is small, theta will be big, right? I can even sketch quickly, right? So let's say we have, this is our scattering center, right? So this is auxiliary line. So, and if S is like this, small one, right? So then scattering angle is going to be large. If S is larger, scattering angle is going to be smaller. So let's say this is S1, this is S2, and this will be theta 1, and this will be theta 2. You see, as S increases, theta is going down. So the derivative ds over d theta is negative. But of course, sigma cannot be negative number. Sigma is just the area effectively, right, in terms of units. So this cannot be negative by nature. So this derivative, this minus sign of this derivative must be dumped, manually chopped, right? Okay, now it should work. And now we can frame this. So now this is the final formula, and that's what people use in order to find differential cross section. Maybe I should write a something like sigma is positive and ds over d theta is negative. Right. So that's why we put an absolute value. Okay, I just want to emphasize on that. Okay, so now let me check what else I need to mention over here. No, pretty much now we have the expression, and so now the next step, of course, we need to get the formula expression which will relate s and theta. Right. Once we have that relationship, we can shove it here, differentiate, massage it a little bit, and we should be able to get sigma. So now the goal is to find the relationship between s and theta. And I'm thinking, can I continue here? You know what? Probably I will move to that side because I will now need another nice picture. All right. And then when I need, I can move to this side. So now I can put a new bullet. So now we need to get a relationship, right, between s and theta. Oops. S and theta. Okay, so how can we get that? S, it's a parameter describing trajectory of the particle, right, at infinity, at the initial infinity. Theta, describing trajectory of the particle at the opposite infinity, right, when the particle goes to our targets, or the targets, detectors, right? So pretty much it means that most likely we should be able to connect them if we look at one of the trajectories of one of the particles. So let's just pick a completely arbitrary particle, draw a trajectory, and see how can we connect these two parameters. Right? And we're going to consider a repulsive case for simplicity, right? And then, okay, attractive case, I will just briefly mention when we actually get the Rutherford's formula. But for now, let's consider a repulsive case, right? All right. Consider, all right, repulsive case. Yeah. And as I said, let's pick one of the particles. So now I need a nice picture. So let me estimate the amount of space I think I should be able to do it here. Yeah, okay, so let's say this is our scattering center target. Right, again, I need this auxiliary line. And particle. So let's assume that our particle first flies along this asymptote. Okay, almost horizontal. Right, and then let's assume it will be scattered along that direction. But of course, you remember particle is not going to fly along this line. Of course, it will be shifted by the S. Here S and here there will be S, right? So it will fly along that line. Okay, almost parallel. Okay, so now I can draw the trajectory. Right. So it will be something like this, right? And of course, our parameters which we want to relate, of course, here it's S, right? The impact parameter, and scattering angle is going to be here, right? So I can draw it. I think I drew it here, yeah, because I can draw it all the way, but let me keep it smaller. Okay, and again, careful guys, use capital theta, don't use small theta, because now we will have to also use small theta in a few minutes. All right, so that's here R infinity. Then this point, let me show. This is the closest point, right? This point is called periapsis. Maybe I can label. So it's R sub m. M stands for minimum. So it's a periapsis. Let me write this. So it's a periapsis, right? Then, of course, relative to this line, relative to this point, relative to the point, relative to the line which goes through the periapsis, the picture is symmetrical. What we have here and there must be the same, right? So it means that let's introduce auxiliary, auxiliary angle, which we will use only maybe for 10-15 minutes, and then we will dump and forget about that. Let's introduce this angle psi, this psi, and of course this angle will be also psi. Because of the symmetry, they are the same, right? And again, we want to find a relationship between theta and s, but theta and psi can be connected easily, right? Since this is angle pi, so theta will be equal pi minus 2 psi. So we can write that theta equals pi minus 2 psi. So basically now writing this, it means that we need to find the relationship between this psi and s, right? Instead of finding now a relationship between theta and s, we need to find between psi and s. So then probably now we have an equation, actually not an equation, we have an integral, right? You remember, which describes this trajectory. At the end of the previous class, no, yeah, at the beginning of the previous class, we derived that integral. So we will have to use it. We will have to use it, right? All right, so let me write, recall an integral which describes this trajectory. This trajectory, right? Which was, okay, let me try to recall it. So d theta, right? You remember now, this is small theta. It's a small theta, which is measured, okay, so basically, effectively, that is the x-axis. This is y-axis, and of course in the classical way, conventional way, theta is measured that way, in a counterclockwise direction from the plus x direction. So that's theta. So that's theta capital, has completely different meaning. Of course, it would be better to use different notations, but that's what is used in the book, right? Okay, so this theta, and then integral of, let's recall dr over r squared, and then square root of 2me over L squared, yeah. 2me over L squared minus 2mv over L squared and minus 1 over r squared. I think it looks like this. Let me check my memory. Yeah, that's the integral, right? Okay, so now the question, of course, which limit to use, because limits just basically defines, right? So we're going to which point is going to be used as, for example, here, initial point and the final point, right? So since we want to relate s and psi now, so basically, psi is connected to this point, periapsis, right? S is kind of most likely can be involved in the particle, in the description of the particle when the particle is at that infinity. So it looks like the most convenient point, this will be our initial point, lower limit, and this periapsis will be our final point and upper limit in this integral, right? So let me, right, so this will be my initial point, right? And this will be our final point at the periapsis, right? And so now let me write coordinates at initial point. So when the particle is here, of course, r equals to infinity, and theta, okay, r naught probably, and theta naught, since it's initial position, right, of the particle, and lower limit. And initial angle, again, theta small is measured from there. So theta naught equals to pi, right? So this is theta naught. Maybe I should write over here. So it's a theta naught equals to pi. Okay, so so here it will be pi lower limit, right? And here lower limit will be from infinity, right? So now the final point and upper limits. So the final point, of course, r equals rm. M stands for minimum, and theta final will be equal to what? Theta, it's this right angle. So this theta, which is what? This angle psi, here psi, so it will be pi minus that angle. So psi will be theta, pi minus psi. So it will be pi minus angle psi. You see, again, the whole angle is pi, but if you subtract this small, which is here also, you will get that angle, which is angle defining direction to the periapsis. Okay, so it means that here we'll have pi minus psi, and here are m. So that's the integral. So now, look where, okay, obviously psi will appear immediately on the left-hand side. S, where S can be in this integral? It's possible that this periapsis might have S, but for now we cannot say. We will have to look at a particular case in order to get in order to see if S is involved there, right? Then M constant, E is constant, V of course doesn't depend on S. V it's potential energy, right? L might have S. Right? So in a few minutes, we will have to dive into L in order to reveal the presence of S in that L. But for now, let me just simplify it, because now, yeah, we have a chance to simplify it. And then we will write L in terms of S. Right. So first, of course, here we will get minus psi, but of course minus I will move to that side. So it will be psi equals, and minus will move to this side, to the integral. So of course I will flip the limits. So it will be integral from Rm to infinity, and dr, and I will just have to rewrite this integral one more time. L squared minus 2mv over L squared minus 1 over R squared. Okay, so now it's a first step in the adjustment. And probably now I will change, replace L, and then I will change the variable. Okay, so now let's connect L. And L is constant, right? So L equals to constant. And let's look at the particle at this infinity to relate S and L, right? Right. L is constant, and look at when R equals to infinity. When R equals to infinity at this constants, of course, we can write that L equals R perpendicular times P, and of course it's at infinity. Okay, I'm using physics one stuff, because of course I can write R cross P, right, and then play with angles, right? So you can do that easily, right? I just use high school first physics one. Right, R perpendicular times P, and of course at infinity. R perpendicular, it's this impact parameter, right? Because R perpendicular, it's a distance between the line of motion, right, and the origin, which is of course origin is at the target, right? So R perpendicular is of course S, and P, of course, it's mv naught, because we are at infinity, where velocity, of course, v naught. Of course, v naught is not given. We need to write it in terms of the E, in terms of total mechanical energy, right? So let me open my explanation box. Of course, E equals mv naught squared over 2, right? So, of course, here v naught will be equal to what? Square root of 2e over m, right? Okay, let me close it. So shoved it here, and of course, you will end up with L equals to m gets cancelled. It will go into numerator under the sign of square root. So s equals to square root of 2me. So that's the connection. That's the relation between L and s, right? So that's what we need to plug into our integral, right? Right. So put in the integral. Right. Okay, so now I think, yeah, we need to, you know what, let me frame this a little bit, because in a few, maybe like in 10, 15 minutes, I will need it again. Although I don't know, maybe I will have to erase it by that time. All right, so of course we can rewrite, we have to rewrite psi equals, rewrite that integral. So of course it will be from periapsis to infinity. dr still always, everything is still there, except for now. Okay, let me write 2me divided by 2me times s squared. Hold it. No, it's correct, yeah. I'm taking s outside, as I said, right? So I moved it in the denominator, and as a result, over here, I will have just 1 minus v over e. V, of course, it's some function which will be given if you, it depends on the system, it depends on the scattering center, right? So, and then minus 1 over r squared c squared, right? Okay, so that's the new integral. Let me check that I got the right one first, and then next manipulations, right? Yeah. Okay, so next, of course, great integral except for this r squared. And I think you remember from the previous class, we already used that substitution, how to get rid of r squared. We need to change the variable, and with u is 1 over r, right? And then this dr over r squared, it's a minus du. So here, what if you take du, it will be equal to minus dr over r to the power of 2. Right. As a result, we can rewrite it in terms of u. And of course, the limits will be adjusted. So it will be from which is the reciprocal of periapsis. The upper limit will give us 0. S stays, minus also. You know what, guys, let me flip integral immediately. I just don't want to rewrite it one more time, right? Because lack of space, you see, we have minus, and we have integral from to 0. But of course, let me flip it immediately, right? You follow it. I will just dump that minus 0 to right? Okay, so and it will be s du and divided by our square root, which is 1 minus v, of course, is the function of, okay, function of u now, it should be, of course, right? V is the function of u divided by e, and minus 1 over, oh, you see where I made a silly mistake. When I factor out s, this s squared should be upstairs, not downstairs, right? You see? Yeah. S squared, yeah. So because now I'm getting something which doesn't look familiar, right? So it will be u to the power of 2 times s to the power of 2, and I can close the square root sign. Okay, so let me check if I got where I'm supposed to be. Yep, that's correct. So that's our psi. Okay, let me write over here. So that's our psi. I thought about framing, but no, right? So now we have what? Relation between psi and s here, s there, and possible s dependence inside of but right now we cannot tell. in next when we start looking at a particular example, we will see if there is a S dependence over there. But anyway, it will be here. Right? It's right now not revealed. Okay, so now plug it back, and we will get the formula which we are going to use to find the relationship between theta and S. Right. So as a result, I can write, so over here, theta equals to pi minus 2s. Of course, I can take outside of this integral from 0 to um and du divided by this big sign of square root sign. So 1 minus v over e minus s squared u squared. All right. Okay, let me check one more time. All right. Yeah, I should have written that it's a function of s. You know what? Let me write it's a function of s, right? Because it's a final result, and it's better to have everything. Okay, so now, of course, yeah, this must be framed. Because it's a crucial expression. Right. Because what? This is basically expression how we can find differential cross section, which has all information about the how particles are going to be distributed, right, on our target. And of course, here we need the relationship between S and theta, and that's what we found. So every time you'll have to use first this, get relationship between S and theta, then shove it here, get sigma, and then you're ready to start analyzing your results, right? Trying to extract information about the scattering center or target, right? Okay, so now basically we just need to pick a particular potential V and get through all this mess, right? So, and of course, we're going to reproduce the Rutherford's formula, right? Which I don't know, actually, he derived or somebody else derived for him. Actually, I need to know, I'm just curious, right? Because he definitely ran experiment. He bombarded with alpha particles, right? Some heavy molecule, I mean atoms, right? And then the Rutherford's formula helped to describe, to explain what he observed, right? But I don't know who derived. Maybe he derived. Shame on me that I don't know that. All right. I will have to start. I will have to erase this. Yep. So we are going to assume, of course, Coulomb potential, and we're going to use repulsive. But of course, at the end, we will see that there is no difference if you use a repulsive or attractive potential. Repulsive easier to draw. I guess that's the reason why repulsive potential is used every time to derive it. So let me write first Rutherford's formula. Okay. Right. So, and again, consider a repulsive scattering. So repulsive scattering. And the potential, of course, will be K sum Z times E, right? Let's say it's an incident particle. Then, because E, it's a charge of an electron, basically. Then Z prime times E, it's a charge on a target, over target. and of course divided by R. Right. And so let me check if should I mention anything. Yeah, Coulomb field. Maybe I should write Coulomb field. Right. Okay. Of course, no one wants to drag all these constants. So let me label denote as gamma. It will be K z prime e squared. Right. As a result, our potential energy will be gamma over R. And of course, we will have to also introduce u as 1 over r, because it's more convenient variable to get through math, or through mathematics, through math. So it will be gamma times u. Right. Okay, so that's potential. And so from now on, there wouldn't be any physics. So we just need to first shove it into this integral, take it, then back to sigma. So after this, physics is over, I can say, right? So probably, let me write V and frame this, because from time to time I will have to go here. Right? Okay, all right. So let me just rewrite it in explicit form. So that will be theta capital, right? Equals pi minus 2s integral from 0 to um and du divided by 1 minus, okay, v, it's gamma, okay, we're already using u, so it will be gamma u over e and minus s squared u squared. So explicit form, right? And so, of course, we will have to take integral, right? Sooner or later. But before we start taking integral, there is a very big question. How can we find this reciprocal of periapsis? So basically, how can we find that shortest distance to the trajectory? Right? So, and let me put the big bullet. How, okay, question, how can we find Rm, or of course, Um? And in your homework, there will be, of course, similar question, right? And we're going to use, in order to find it, we're going to use conservation of mechanical energy. And which point should we use as initial and the final point? At infinity. Basically, we know the total mechanical energy E. In any experiment, E is the given constant, basically, right? Depends on how you set up the experiment. So it's your contribution to the system, right? E capital. And that's what particle has when it is at infinity, right? So we're going to use conservation of mechanical energy and compare total mechanical energy at infinity and at the periapsis. Right? Okay, so let's write it down explicitly. Of course, at infinity is just E. And at the periapsis, of course, a couple of classes ago, we wrote this mr dot squared over 2 plus L squared over 2m r squared. And then potential, it was what, plus and yeah, gamma, plus gamma over r. So that was our potential. Oh, rm subscript, which is of course important. As I said, we're going to look at the periapsis, right? So what's the most characteristic feature of a particle when it is at the periapsis. Unique piece of information when the particle is at periapsis. R dot is 0. R dot is 0 because at that point R doesn't change for a moment. Only we have only direction in the phi velocity in the phi direction, right? So that's the major feature, and that's what we have to use. And of course, in your homework, of course, you will have to go through this ordeal. All right, okay, so let me rewrite in terms of u, of course. All right, so it will be L squared over, and also, let me, yeah, that's why I framed. So now I want to use this, right? Of course, I want to write it in terms of S and E. And you see S will be involved, as I was telling over here, that it's possible that UM depends on S. And you see now, once we shoved instead of L, this S will appear. Okay, so now also let me write that I will use that fact that L equals to S times square root of 2ME, right? And probably I will write underneath E equals, so it will be S squared times 2ME. Okay, this 2 looks too fat. Let me make it look more elegant. Divided by 2m. And of course, R squared gives us UM squared. And plus gamma times UM. Okay, so 2m goes. Something. No, it looks everything seems to be correct. I think I moved S squared to somewhere. No, everything is good. All right, so it will be E S squared UM squared plus gamma U sub M. Right. So effectively, what is this? We need to solve for U, right? For U sub M. It's a quadratic equation, right? Right. So of course we can divide everything by ES squared. Right. And of course we will end up with UM squared plus gamma over ES squared UM and minus, yeah, this goes there with minus, so it will be 1 over S squared. 1 over S squared equals to 0. Okay, let me check if I got the right quadratic equation, right? Yeah, that's the right one. Okay, so now let's just write down the solution. So it will be UM. You know what, I'm afraid that I will run out of space. Let me write underneath. So UM, of course, two solutions, so it will be minus gamma over ES squared plus minus square root of gamma over ES squared to the power of 2. Then minus and minus from here will be plus, so plus 4 divided by S squared. And then also 1 over 2. Let me put that 1 over 2 over here. So I'll put 2 and 1 over 2. Okay, so now let me rewrite it. So it will be minus gamma over 2E S squared. Okay, which sign to use? Which sign should we use? Plus or minus? I think it's obvious because UM, yeah, it's a reciprocal of periapsis, reciprocal of a definitely larger than 0 value, right? So it must be positive, right? So in order to have positive, of course, minus must be dumped, right? So we have to use only plus. So the meaning of the second solution, I don't know, maybe it's there's some imaginary trajectory over there, so mathematically it's hidden, right? So only plus, of course, will be used, and So, and also 1 over 2, I will move inside. So I will get 2 will appear here and in this bracket. Right, so it will be plus square root of a gamma over 2e s squared to the power of 2 plus 1 over s squared. So that's the solution. Now, let me introduce, let me denote a construction as a certain parameter. You will see when I start taking integral, exactly the same parameter will appear one more time. And just to reduce amount of writing, let me do it. Right? It's not a crime, but it will make my life a little bit easier. So let me denote, just for fun, right? Denote as a 3 lines. Basically, that's how I define this a. It's not a semi-major axis, nothing. It's just a parameter. Let me denote as gamma over 2es. Okay, let me frame with bracket. I mean with black, because again, you will see at some point in maybe in 10 minutes I will need it. Okay, so denote I the right thing. Yeah, so that's correct. And of course now I can write u sub m. The solution will be, so it will be minus a over s, because here we have s squared, so one s left for the denominator. Okay, let me write it better. And then plus square root of, again, it will be a over, I think s squared, should I take it outside? No, I leave it like this. Yeah, so pull it. No, good. I doubt myself sometimes. So it's a over s squared, a over s squared plus 1 over s squared. Okay, so that will be our reciprocal of periapsis. Right, so let me frame it with blue. Again, it's not final, but we will need it. Of course, at some point when we take the integral, of course, we will have to shaft. We have to use the upper limit. Okay, now the hardest part. So let's take care of this integral. Right. And since you're going to have a similar integral in your homework, let me get through this integration. Right. In the past, some students said, okay, it's good that we had, because I know students hate taking integrals and they do everything possible to avoid it, right? And sometimes they run into some troubles, right? Like tables give you the value of one integral in terms of natural log, but it can be also written in terms of arcsine. But then they have troubles how to get from natural log to arcsine. Some you see some funky moves, right, in order to make the transition, right? Right. So now back to our integral. Yeah, and again, as I said, in your homework, you will have to find periapsis point in exactly the same way, right? Okay, maybe I will put here, this was a sort of digression, a bullet, and now back to the integral. Back to the integral. And you know what? I'm not going to rewrite integral. Basically, let me start with massaging this denominator, because that's where the trouble, well, not the troubles, that's, yeah, that's the most difficult part. So basically, we need to complete the square in this, in the denominator, right? Okay, so now, yeah, I'm not going to rewrite integral, right? So let me write, so we're going to complete the square. Right. So square root, no, without square root. Let me complete without square root, and then of course I can put that square root on top of. So it will be 1 minus gamma u over e, and then minus s squared u squared. Okay, so let me start rewriting it. So it will be 1 minus gamma over, okay, let me keep u here. All right, so e, then I'm going to multiply by 2 upstairs and downstairs, right? Then minus s squared u squared, yeah, we'll keep it, and then plus gamma over 2es squared and minus, and then we'll see if it works, gamma over 2es squared. Okay, I just added the same thing and subtracted the same thing, and here multiply by 2 and divided by 2. And which terms I'm going to use? I'm going to use this term, then of course this one, and this one. I'm going to try if it gives me a square. So it will be, of course, minus outside, so it will be SU, or US, yeah, US sounds better, right? US and plus gamma over 2ES squared. Okay, I think it should work. It looks like it works, right? So what will be left? This one and that, so let me rewrite these, which are going to be untouched. 2ES squared and then minus, okay, let me write, so US and plus gamma 2ES divided by 2ES and squared. Okay, so let's square it. So this will give us this, then this will give us that, and the cross term 2 will disappear. It will be, S will disappear, so it will be gamma U over E. Yeah, exactly. So it works. Okay, and now I think now it's time to recall this parameter, because I don't. You see, we have exactly the same structure: gamma over 2ES, gamma over 2ES. So let's write it in terms of A. All right. So it will be 1 plus A squared, right, and minus US plus A n to the power of 2. Okay, let me check if I'm getting, all right, the same thing before I got into deep troubles. No, everything seems to be good. Seems to be good, right? Okay, so now let me factor out 1 plus A squared. So it will be 1 plus A squared, and it will be 1 minus US plus A divided by square root of 1 plus A squared, and the whole thing is squared, and another bracket. Yeah, so I factor out this. I put it inside of this square, so that's why square root appeared, right? Okay, so it looks like we are ready to go back to the integral. So we can shove it here and then finish this integral. Okay, so I need to erase this picture. Let me think. No, I don't need anything except for this integral eventually, yeah. Because as I said, once you derive this, right, now it's there's no physics. You just take a potential, plug it into the formulas, and start massaging them, right? That's it. So at that point, you're not a physicist, you're just a mathematician, right? Okay, I will just keep the integral, I mean, this formula. I hope I will have enough space to, before I have to erase this. Okay, so now back to the integral again. So this, and you know what? Probably I will just write only this integral without this mass, right? I will add that later, right? Yeah. So wrong color. And S, even S, I will also keep outside. So only that. So it will be integral from 0 to um and du and square root of that 1 plus A squared. Okay, let me take the square root separately. That square root declared independence, right? And 1 minus US plus A. Okay, this bracket is too short. Let me increase it. Divided by square root of 1 plus a squared, right, and this. Okay. Oh, to the power of 2. Whew. Now it looks definitely better. It looks messier, but definitely better from the mathematical point of view. Because look, we have here u. What if I just multiply by s and divide it by s? No crime. So far, everything is legitimate. Then I have here plus a. A is the constant. I can add a and put it in a bracket. When you take a differential, a will disappear. Again, no crime. And then now you see what we have. We have us plus a and this square root. And here we have exactly the same thing. Let's introduce new variable, z or psi, whatever. Let's call z. Basically, I'm just using substitution, right? So let me introduce. I think I use z. Let me check. Yeah, z. So it will be us plus a divided by the square root of 1 plus a squared. Right, okay. Closing my explanation box, and it will be equal 1 over s. Then, okay, you know what? Now, for a few steps, I'm not going to use right upper and lower limit, because I just don't want to rewrite it in terms of new variable. When I get back to the original only then I will restore it. I'm just lazy to do steps which are not needed. Right. So as a result, we'll have dz over square root of 1 minus z squared. Wow, that's the piece of beauty now. Of course, now everyone knows that which substitution we have to make, right? For example, cosine. It's a classical, right? So now classical, so z is cosine of psi, for example. I like how snaky this psi is, right? Okay, let me check that if I'm still on the right track, but it feels like okay. Yeah. Okay, of course, dz will be equal minus sine psi d psi, right? And of course, we will have 1 over s dz, okay, minus I will take outside. Again, no limits. Sine psi d psi, and then 1 minus cosine. Of course, it will be sine, and then square root. It will give us another sine of psi. So everything is falling apart. Looks great. So of course, integral of d psi, it will be just psi. So it will be minus psi over s. Okay, the limits, but of course I'm not going to write anything. I will start restoring the original variables, right? So psi, it's arc cosine of z. So let me write minus 1 over s. Then arc cosine, it will be cosine to the power of minus 1 z, and z, of course, that mass. So it will be us plus a divided by square root of 1 plus a squared. Right. And now, yeah, we're back to u, and of course now we have to write limits from 0 to um. Okay, so now, okay, so I'm thinking, should I plug here first and then go back to that integral? Yeah, let me plug here. Because we see this is our framed. So now that's what we have to use over here. Okay, so now we'll need space. So let me write here, start from the new line. Big bracket. Cosine, okay, arc cosine of. Okay, now we have to be careful, right? Okay, let me write first a. then plus u times s. Okay, let me write s and times u. This is minus a over s. Okay, a merged with, so it will be minus a over s, right? I just flip this numerator, right? So changed order. All right, and then plus the square root plus square root of a over s squared plus 1 over s squared, right? That's numerator. And conservation of brackets, very important. Okay, so upstairs there is fine. Then divided by square root of 1 plus a squared, right? It's the upper limit I think I applied, if I am correct. So far I don't see any troubles, right? Okay, so now let me apply the lower limit and then I will take care of this mess. So minus arc cosine of, outside people are cleaning the corridor, vacuuming, if you can hear some noises. Right. So 0, 0, 0. This is 0, so it will be just a divided by square root of 1 plus a to the power of 2, right? Okay, so and now again, conservation of brackets, we close this, close that, so we need to close this square bracket. Okay, so now this s gets cancelled, so as a result here we'll have plus a and minus a, so as a result this and this goes. Promising. Then, of course, this s enters this square root as s squared. So as a result, this s squared and that s squared will be cancelled, right? So this and this and this will get cancelled. As a result, what we have under, so here we have nothing except for square root of 1 plus a squared. And here 1 plus of a squared square root. So basically we have exactly the same numerator and denominator. So this whole thing, this whole thing equals to 1. And our cosine of 1 is 0. Beautiful. I like when such a mass disappears or gets evaporated, right? That's such, gives us such a nice feeling, right? Of success, right? So this will be just 0. The whole thing will be just 0. All right. Okay. So now, oh, minus and minus, minus also disappears. Just a lucky day, right? So we'll have as a result 1 over s and arc cosine of that ratio. And of course, with that ratio, we cannot do anything except for rewriting it. So that's our this integral only. You remember, we still have this left. Okay, this part left. All right. So now back to actual original integral. So back to the original integral. Right. Okay. So let's start rewriting. So it will be theta equals pi minus 2s, right? And this 1 over s and arc cosine of a divided by square root of 1 plus a squared, right? Okay, s of course goes. And so now let's rewrite it in a different form. Probably I will take this term to that side. I will have theta goes to that, so it will be pi minus theta divided by 2, and that will be equal to arc cosine. Okay, and let me take immediately, get rid of arc cosine. Take a cosine of both sides. It will be cosine. Oh, just a second. Let me get at least the pi minus theta over 2 equals to what we have into that bracket. So a divided by square root of 1 plus a squared. And of course now, at this point, we need to recall what is a. You know what, probably I will take a. Okay, let me take a downstairs. Right. Less stuff I will have to rewrite. So square root of 1 plus 1 over a squared. Okay, and now let's recall how we denote a. So it will be 1 over divided by square root of 1 plus. So we just need to flip it and square it. So it will be 2e f divided by gamma n to the power of 2. That's that's it. All right. Okay, it's not the end, and I think I need space, and most likely I wouldn't be able to. Ah, we have this. We already rewrote it. We've been using it. Right. Okay. So now, cosine pi over 2 minus theta over 2. We can change to sine, right? So it will be equal to sine theta over 2. And since it's a first quarter, it's a positive sign. A trig identity. Then it's a first trig identity, right? And then second one, sine can be connected with cotangent. The next one I usually don't remember, right? But for the class, of course, I refreshed it. If you don't use something, of course, you tend to forget it, right? So it will be 1 plus cotangent. Okay, it's not cosine, it's a cotangent, right? Of theta over 2, right? Theta over 2 square. Yeah. And close. Am I right? Yeah. Okay, so it's just the left-hand side, but the right-hand side, still that. So it is equal to 1 over square root of 1 plus 2es over gamma to the power of 2. And now you see immediately that structure is exactly the same, so it means that this must be equal to that. Right. So, and we're almost ready to write the final relationship, right? So it will be cotangent of theta over 2 equals to 2es divided by gamma. Right. And what we want to, in the formula which I erased, we will have to differentiate s with respect to theta. So let's write s explicitly. So from here, s will be equal to gamma over 2e, gamma over 2e times cotangent. Cotangent of theta over 2. Okay, so gamma, it's this mass. Okay, and let's write the final form of the relationship, right? So S equals gamma. Is it just gamma? Yeah. All right, so Z, okay, difficult to write, but I can still think and do better. Z prime E squared divided by 2E. So that's a bunch of constants. Ah, K, forgot K. I think it's the second time it happens. It happens, I think, in the past when I forgot K. This innocent constant. So that's S. And cotangent of theta over 2. Right, so let me check. Yeah, that's exactly. Actually, even in my notes, I forgot K. That's why it's the second time. If I do it by myself without looking at the notes, right, I can get K. Okay, I need to fix that. That's the reason of this mistake second time, right? Okay, so now what's left? So we found this after finding this relationship. So we need to go to the expression for sigma, shove this. We'll have to differentiate with respect to theta, this capital, theta capital, right? And just a couple of lines, like 5 minutes and less than 5 minutes, we will get the expression for sigma. And then, so that will be the differential cross section, right? Which give us information how particles are going to be distributed on our detectors. And after that, of course, logical question, what about the total number of particles which are scattered? Right? So again, that's very simple manipulation. So next class, within like 10 minutes, we should be able to finish this scattering process.